Hey everybody, welcome to our next kinetics video. In the first video we talked about how we're going to talk about the reaction pathway that chemical reactions go through. We now understand if reactions are spontaneous or non-spontaneous. Now we need to get at how reactions actually occur. And one of the key ideas to understanding how reactions occur is understanding the reaction rate. The speed with which a reaction occurs tells us, or could tell us, a lot about how the actual molecular events transpire. So if we're going to understand how fast a reaction occurs, we need to begin to talk about the different kinds of rate information we can get in chemistry. Now let's talk about another science. Let's talk about a fairly simplistic science like, physics, for example. Now in physics, you can measure rate information too, right? You map out the amount of displacement you had, and you divide it by the amount of time, and you call that speed. So all you need is kind of a ruler or some kind of tape measure, some distance measuring device, and a stopwatch, and you can get rate information in physics. In chemistry, it's a little bit trickier, because what we're going to be measuring in chemistry, we still have time in the denominator. We're still going to map out the seconds or the minutes or the hours or the years when we talk about rate information in chemistry. But instead of the reaction going someplace, or reactions don't go anywhere, they stay put, what we're going to do is we're going to measure changes in concentration or pressure, and experimentally that can be a little bit trickier to do, and we'll talk about some of those details when we get together in class. But keep in mind, when we measure rates in chemistry, we're going to be measuring typically change in concentration divided by changes in time. Now I'm going to go ahead and get rid of my face here, and I'm going to get rid of our title so I have a little bit of space to do some work. And we're going to talk about three kinds of rates. We have instantaneous rate, average rate, and relative rate. Now, I'm not going to spend a lot of time talking about the first kind, instantaneous rate, but let's spend a little bit of time talking about it. Instantaneous rate is going to tell us how fast is a reaction right at a given moment. And so you can see over here I've got an example of a reaction. I've got the decomposition of nitrogen dioxide that I alluded to in the previous video. So NO2 going to form NO and O2. If I want to figure out the instantaneous rate, I'm going to have to do some calculus. Now, we're going to not spend a lot of time doing calculus in this unit, although we will spend some time doing calculus. Don't worry about it. It's really going to be about knowing how to use the results of the calculus, not the actual calculus itself. But essentially, instantaneous rate we can kind of show on the graphs here. So here is the curve for NO2 going away over time. NO2 is a reactant, so its concentration is going to go down over time. Here's the concentration of NO growing in over time, and here's the concentration of O2 growing in over time. So if I want to measure the instantaneous rate, what I'm really asking is, okay, how fast is the chemical reaction proceeding, say, exactly at that moment in time? At the, say, 240th second, how many moles of NO2 are going away per second? That would be an instantaneous rate. And we will come back to that idea a little bit later. For example, using instantaneous rate information, we'll be able to ask, okay, how much product is formed after 53 seconds? How much reactant is left at the 1 hour and 13 second mark of a reaction? So we'll come back to that a little bit later on when we talk about rate laws, which will be the subject of our next video. But what I'm going to spend the time here now talking about is average rate information. Now, average rate really describes what you can see here in the green line right there, right along that curve right there, okay, where we have a big change in time and a big change in temperature. So the formula we would write out for an average rate would be something like the change, let me get my pen going here, the change in the concentration of NO2 over the change in time. And so we might be talking about over the course of 100 seconds, how much has the NO2 changed over that block of time? That would be average rate. And I could calculate the average rate of something like O2 or the average rate of NO, so delta concentration over delta time. This is one of the rates that we'll spend most of our time talking about. Another kind of rate information that we could get would actually have to do with relative rates. And this is kind of important in chemistry, because if we know how fast the reaction is with respect to one of our reactants, we'd like to know how fast the reaction is with respect to another reactant. So, for example, if I know how fast this reaction is with respect to the NO2 decomposing, going away, I might want to be able to turn that into rate information for how fast the NO is forming, or how fast the O2 is forming. And you can see the relative rate information in the relative shapes and changes of our curves here in the diagram on the left, in our concentration versus time. So let's take a look at this. I'm going to write out a statement here that shows the average rate of change of NO2 over time. Now the question is, how do I equate that to, say, the average rate for the change in the concentration of NO over time? Well, if you look at the balanced reaction, you see that every time I consume 2 moles of NO2, I generate 2 moles of NO. Or seen on the graph, the curve of the NO2 is going away as fast as the curve for NO is growing in. So this is relative rate information. For every 1 mole of NO2 that goes away, I generate 1 mole of NO2. Pretty straightforward. But now let's do this in terms of another relationship. For example, how fast, let's see if I can get rid of this here, I'm going to write another relative rate statement. What if I have the change in the concentration of the NO2 over time? How do I equate that to the average rate for the formation of O2 over time? So change in concentration of O2 over time. So if you look at the stoichiometry here, every time I consume 2 moles of NO2, I generate 1 mole of O2. So the question is, how do I equate these statements? Because right now they're not equal. Well, the way I equate them is I'm going to need to take my average rate of NO2 and I'm going to need to cut it in half. Okay, put a fraction of 1/2 in front of it. Now there's another thing I need to do, and I made this mistake actually in the previous relationship. These aren't actually equal yet, because the NO2, as we can tell, is going down in time, and the O2 is growing in over time. So to really make these two statements equal, I need to put a negative sign in front of the NO2. I would also have needed to put a negative sign in front of the NO2 when I equated it to the change for the average rate of NO. So now this is relative rate information. And the trick to writing relative rate statements is to use the coefficients in the balanced chemical equation as fractional coefficients in front of each average rate statement. So if I know then the rate of the reaction with respect to NO2, I can figure out the rate of the reaction with respect to the O2. And this is important because in chemical experiments, we don't always have the ability to monitor all of the ingredients of a reaction. Maybe I have an oxygen sensor so I can detect how fast the O2 is growing in, but I don't have a way of directly accessing the concentration or pressure of the nitrogen dioxide. But thanks to an average rate, relative rate statement, I can equate the two. All right, so that's a little bit about the kinds of rate information that we're going to get in chemistry. Next up, we're going to talk about ideas referred to as rate laws, and this is where we're really going to start to dig into some experimental data and the kinds of data we need to collect in order to do kinetics.